Hey there, in this video we are talking about class templates and the standard template library in C++ programming. And this covers sections 16.4 and 16.5 in the Gaddis textbook. So in the last video we were talking about function templates. We take one single function and instead of making a whole bunch of versions of that does the same job for different types of data, just make one version that receives, as the parameter, receives an abstract data type. You actually leave the incoming type basically as a variable. And then at that point, the application programmer can choose to send in any type of data that they want, and the function will just handle it. Pretty useful. So what we're going to see here is an expansion of that idea, is you can do the same kind of thing with an entire class. Make an entire class templated, and then all the member data becomes abstract, and all the public functions are working with abstract data. And again, the application programmer can choose to store any type of data that they want in there, and the whole thing just automatically works. So very useful, very handy, and I'm glad that this is in C++. Let's take a look at this. So class templates. So yeah, classes can also be represented by templates, and when a class object is created, the type information is supplied to define the type of data of the object. Again, when the application programmer instantiates one of these things, they're going to specify what type of data they want to use, and the compiler is going to spot that and on the fly automatically create code for that particular case. Now, unlike functions, classes are instantiated by supplying the type name at object definition. So with functions, you just had to call it, pass in some kind of parameter, and the C++ compiler could figure out what type of data that was by the incoming parameter. Now with class templates, the application programmer is actually going to have to specify what type of object they're declaring because there's no parameter there for the compiler to clue in on. So there's just one little extra piece of typing where you do have to specify what type of data I want to store in my templated object. Okay, so here's an example of this. Here is a templated class, and the class is called grade. Of course, you can see the template prefix. That looks exactly like it did for function templates here. So keyword template, class T, there's that abstract data type. When the application programmer uses that, that's going to turn into integer or float or character or something like that. So it's a class to store a grade like you get on an assignment in a college course, of course. So here's your private data. There's a score of type T, right? An abstract data type. There's going to be a constructor that receives a variable of type T incoming to store for the score. Here's a mutator called setScore that receives a parameter of type T. And then when you call the accessor getScore, it's obviously going to pass back a value of type T, whatever you stored there. So the great thing about this great example here is if someone wants to use integers for their grades, this class will totally handle that. If someone wants to use doubles for their grades with decimal components, this will work for that. If someone wants to use characters for their grades, A, B, C, D, or F or something else, this will also work for that as well. Okay, so any type of thing you want to store for your grades, this will actually work for the application programmer. Let's take a look at a couple examples of what that would look like. Okay, so you see here highlighted in red is what it looks like when you instantiate one of these grade objects. As you write down grade, name of your class, and then angle brackets and the type of data that you want it to be storing for its member data. And once again, the compiler sees that, and when it sees that, it knows, oh, I guess I have to create a version of the grade class, right? I'm going to automatically create code and compile it for all that data and all those public functions, all those member functions that are going to be working on data of type integer. So I normally read that as a grade of type integer. And here we are creating one of those things, right? Creating an object called int grade, passing 60 into the constructor. And then once you do that, storing integer 60, you can change the score by calling int grade.setScore80. You can access the score that's recorded by calling int grade.getScore, right? All that kind of standard stuff. Here's an example where we're creating a grade of type float. So going to that grade class and making it store a float in this case. And then we're calling it float grade, calling a constructor with some decimal, and then you can call floatgrade.setScore. You can call floatgrade.getScore, and that's handing back a float in this case. But again, if you want to store characters there, A, B, C, D, or F, this will work there. So here we're declaring an object of type grade of character, grade of type character. Calling it the char grade, storing a B in there to begin with, calling chargrade.setScore to change it, calling chargrade.getScore to access it, stuff like that. So that's what it looks like when you are instantiating an object from a templated class. Put down the basic class name, angle brackets, the specific type that the application programmer actually wants to use in this particular instance. And the compiler sees that, creates code automatically for that kind of class. Great. All right, now here's a little bit of an awkward thing with class templates. The question is, where do you put the implementation code? Where do you put the code for setScore and getScore and the constructor? Now, if you remember, templates are only creating a pattern. If I make a templated class, just like with templated functions, that's not actually code, it's just a pattern for the compiler to follow when it finds out that it needs one of those things. So you can't take the templated class and directly compile it to object code. Again, if I just made a CPP file and tried to compile it to an object.o file, it would be empty, it's nothing. Not until you have some code that actually creates one of those objects and specifies a particular concrete type can the C++ compiler know, oh, I need to actually make code of that type and compile that. So you need the call, right? You need the object instantiation code before it knows what type of thing to actually create. So if you do what we normally have done in the past and put the implementation code in a separate CPP implementation source code file, that's not actually going to produce any code, right? That CPP file won't actually produce code because it won't have any instantiations of the objects. So instead, one option, what we'll be doing here and what the book does, is we'll put all the implementation code in the .h header file. Just for templated classes, put all the code in the .h header file. Could be inlined, could be separate, whichever one you do. We're going to put it on the header file so that when you pound include that header file in code that wants to use that kind of class, all the code will be visible from the pound include, and then the compiler can see the creation, see what the pattern is, and then automatically create the code that you need. So you do that, and then you will have access when you include it to this code that's all entirely in the header file, and the compiler will generate the specific type code as required. So a little bit awkward, I wish it wasn't quite like that, but that's what we're going to be doing in the Gaddis book, and I do think it's, of the bad options, it's probably the best and the cleanest. There's some other options I've seen in the past, and I'll say that as one example, the data structures book that we use in our course by Carano, what they do is they do make a .cpp file with the implementation code, but then over in the header file, at the end of the header file, they pound include the CPP file, which feels backwards from what it's supposed to do, but that actually does work if you think about it. So it is an option, but here in our course, we're just going to put everything directly in the header file. Okay, now how do class templates interact with inheritance, right? We were talking about inheritance and polymorphism and how incredibly powerful that is and how incredibly essential that is to even how the C++ standard library is constructed. Talking about that back in chapter 15. So can you use class templates and also inheritance at the same time? And the answer is yes. So class templates can inherit from other class templates. Kind of short example here. Let's say I have a templated version of the rectangle class. So template class T, class rectangle here. And now the coordinates of your rectangle, they could be integers, they could be floats, they could be doubles, whatever you like. I'm not sure that's super useful, but maybe you do that. And having said that, now we're going to make a specialized child class for squares. And of course, squares are a type of rectangle. So here, we're going to also make a templated class T class square. Here's the colon, here's the class access specifier for what we're inheriting from. Inherit with a public class access is what we do at least in this course. And we're inheriting from a rectangle of type T. And so you have to have that rectangle angle bracket type T here to say that that was a templated parent class. And then all through the rest of your code in Square, you're likewise going to have to use that type parameter T everywhere the base class name is used in the derived class. So now any place you refer back to rectangle, you're going to have to say rectangle type T, rectangle type T, rectangle type T. Like in any constructor that's referring back to it, and in a function that's creating one of those objects, right? You're going to see a whole lot of rectangle angle bracket type T. You're going to need to do that all through the rest of your code when it refers back to the parent class. Okay, so kind of a little sophisticated thing, kind of bear that in mind. Now, I will say that for the course that I teach at CUNY Kingsborough, the very last assignment that I give my students uses both class templates and inheritance. So there's an initial base class template, and I ask my students to expand that in a different way. So they do actually have to do this in my students' last assignment. So I would ask my students to look very, very carefully at this. There's a great example in the book, expanding a particular class that's a class template to begin with. And that actually is the last assignment that I ask for, does both of these things, which I think is pretty good practice for the end of our first year, as a matter of fact. Okay, now, the other thing we want to talk about today is the Standard Template Library, or STL for short. And a big subject. We can talk about this for a long time. We're just getting a little bit of an overview today. So the Standard Template Library, or STL, is a library containing a bunch of class templates and function templates that are already provided to you for frequently used data structures and algorithms. So this is an add-on to the C++ language. It's not technically part of the language, but it's an add-on that's usually provided whenever you download a C++ compiler or IDE. So for example, Dev C++, if you're using Dev C++, when you installed that, you got a version of the standard template library, and it is available for to use. Now, hypothetically, if you're maybe using an older compiler, it may not come with the standard template library. Or maybe if you're working in an environment that has very reduced memory, a very small amount of memory, like for embedded systems, then you might not be using the standard template library there either. But I'm sure that for beginning programmers, whatever IDE you're using, I'm sure this will be available. And unless you get in one of these kind of unique situations nowadays, I'm sure the STL will be available. Okay, what is in the STLs? A whole bunch of stuff, a whole bunch of very powerful stuff. So first of all, containers. Okay, when we say containers, we're talking about objects designed to store a bunch of data. Objects that are designed to store a whole lot of data. They're going to be alternatives to arrays, right? Arrays are your basic way of storing a lot of data. Containers are any kind of object that's an alternative or an expansion or an elaboration to how arrays store a bunch of data. Now, at least in our course, we've seen like at least one example of that in a lab at one point, is we had an object that was designed to store temperature data for a whole month. I think that was one of our labs at one point. Temperature data for a whole month, and it happened to be containing a partially filled array to do that job. So there's a lot of other choices. There's a menu of many other choices for container object types of different ways of storing a whole lot of data that may have different features depending on what you're doing. Now, these containers in the standard template library come in two flavors, two varieties. First of all, there's sequence containers, which are ordered collections. Like if you think back to a mathematics class, like mathematical n-tuples, like ordered pairs, or ordered triples, or ordered four tuples. Okay, some number of things where the order matters. That's what we're saying here. The order matters in a sequenced container. And so some examples of this in the standard template library are like vectors, where there's an object called list, or there's a class called deck. And for what it's worth, deck is short for a double-ended queue. We're going to be talking about all these things in the next couple of videos, actually. So we get a little introduction to each of these different types of things and what their advantages and disadvantages are, the way that they're storing a whole lot of data. Now, the other flavor of containers are called associative containers. And those are things that are unordered collections, like mathematical sets, where the order does not matter. And sometimes that's what you're dealing with. So you want a container that has that behavior. And in the standard template library, some options for that is there's a class called set that works just like a mathematical set. You can store a bunch of stuff in it, and the order doesn't matter. Okay, there's also a multi-set. There's a thing called a map, and there's a thing called a multi-map. Now, these associative containers are actually not things we're going to touch on in this video. Maybe in your data structures class later on you'll talk about these, or maybe some kind of future course. But they do exist in the standard template library. You can see why you'd want to deal with sets some days, and they do exist. But we're going to be focusing mostly on the sequence containers here in the next couple of videos. Now remember, these are all templated classes, just like we were talking about in this video. So if you want to make a vector, you can make a vector that stores a bunch of integers, or a bunch of floats, or a bunch of characters, or a bunch of strings, or a bunch of feet inches objects, whatever you like. They are all templated classes, just like we're talking about here. So a lot of flexibilities. You can store whatever kind of thing you want in it, but different ways of doing that. Okay, now the other major thing that the standard template library provides are algorithms, are templated functions to do any of the different types of algorithms that we probably talked about all in this course and this whole year. So the STL does contain algorithms, functions again, implemented as function templates to perform operations on those containers we were just talking about. So assuming that you've stored your data in one of the STL containers, these templated functions are happy to do their work on one of those things. All of these functions here are in the algorithm header file. So you want to use any of these, you'd pound include algorithm to get access to these. And among the functions that they have implemented in the standard template library, binary search. Okay, how useful is that? We talked about that back in chapter 8. There's a generalized for function that processes everything in a container, whether it's ordered or unordered. There's a function to find a particular item, to search for a particular item, kind of like the searching algorithms we were talking about back in chapter 8 again. There's a function to find the minimum element in your container. There's a function to find the maximum element in your container. I mean, that was sort of the lab we were doing in the last video, actually, a little taste of that. There's a function to sort all the data into a particular order. Now, that would only make sense for ordered containers, sequenced containers, right? That wouldn't make sense for the unordered stuff like sets. There's a function to count how many things are in your container. There's a find function. There's a random shuffle function, which is sort of the opposite of a sort function, in case you want to use that. So a lot of the functions, a lot of the algorithms that we've talked about in this semester, particularly back in chapter 8, isn't that great? They're all provided to you for free in the standard template library. That seems great to me. Of course, in order to use them, you do have to store your data in a container, and then you can just call these functions. It's just built into the STL, and you get that for free with a standard C++ installation. Awesome. Okay, so there's a lot of detail there, and you could look at the details of exactly how you use the standard template library. Again, in this particular video, we're just giving you an overview of all the different incredible stuff that's in the STL, and maybe in a future course or on your own, you could dig into details about how you would actually use this different stuff. Okay, but that's a really broad, mile-high view of the STL. We'll continue to talk about that in future videos, and I'm sure future courses that you'll take. Okay, here's just kind of dig into one little example here. So we'll dig into that initial vector container. Again, that's a sequence container that can store a bunch of stuff in order. So it keeps it in a particular order where the order matters. So this, in STL, there's a library called vector, so you'd have to pound include vector for this. It's a template for a vector. So you can make a vector of type character, a vector of type integer, a vector of type float, like we're talking about. And the primary member functions that you'd probably be using most of the time are in this table below. Now, there's actually more detail in the Gaddis book at the end of chapter 7. The end of chapter 7, there's a fairly sizable section introducing vectors as your first alternative to basic arrays. And I made a lecture video about that. You might look for that video on YouTube to get a more complete story about vectors would probably be a good idea. But for our purposes here, here's just kind of the main highlights of what the vector class provides you. There's a function called size to return the number of things in your vector. There's a function called pushback that accepts a particular argument, whatever you're storing in the vector, and adds it to the vector. Okay? Unlike an array that is a fixed size most of the time, a vector, you can add more stuff to it, and if it has to, it will resize itself and make itself bigger to store your extra information. So that's what pushback does. Takes one piece of data and pushes it on the end of your vector, the end of your list of data. Okay, that is what's happening with pushback. The argument is inserted, added to your vector after the last element. Okay, we refer to as pushing when you're adding more data into a container. You want to remove stuff from your vector. The function for that is called popback, where you're removing the last element from the vector, and the vector looks like it's getting smaller. Okay, so you can add stuff with push, you can remove stuff with pop. And then they've also overloaded the operator subscript brackets. We said you could do that back in chapter 14 when we were talking about overloading operators, and they've done that here so that a vector looks like an array. Right? This actually allows array-like access of existing vector elements. So having put some stuff in your vector, now you can access it by saying name of my vector, square bracket, what subscript I want. And it looks exactly like an array. How handy is that? So whatever we're familiar with for typing down to code through access stuff in an array, you can make your vectors look exactly the same way. Now there's a bunch of other member functions in vector. There's an at function, there's a get function, things like that. But these are probably the most basic things you need to get started using vectors. So we might practice that in a lab or something like that. It is the most basic STL container type. So probably like in your future course, that might be built into other classes. They might expect that you're using vectors. I'll say a lot of C++ professional programmers, when they start to store data, actually the very first thing they're going to turn to for real on a daily basis is they'll turn to the STL, pick one of the containers. They might not actually use arrays directly because that's a very basic data type. They might actually choose vectors first. Okay, so maybe on a daily basis, a professional programmer would just store all their stuff in vectors. Works like an array, but has these additional features here. You can add more stuff to it, among other things. So very, very common, and I think it's smart that they overloaded the subscript operator to make it look like it's an array, but maybe you're actually using a vector instead. Again, there's a more complete story there in the other lecture video about vectors, and you might go look for that on YouTube. Probably a good idea at this point. Now, let's think briefly about how vectors manage to do their magic. This is not something that I would go into in the basic video for first semester programming, but this is our advanced programming course, so maybe it's useful to open up the hood and actually see how vectors work internally. So the technical term for what a vector is doing is called a dynamic array. Actually, there's a lot of names for this. Some people call this a dynamic array, a growable array, a resizable array, an array list. That's actually what Java calls it. So we've been saying you can use a vector instead of an array, but the little secret is vectors actually are still arrays. They actually are holding an array inside themselves to hold their data. So when we say dynamic array, we're talking about a data structure that really allows something that is an array to appear, to grow or shrink or as needed. And how that actually works is a vector has a pointer to a dynamically allocated, partially filled array. So an array that's got some stuff in it, maybe it's got some extra space so you can add stuff to it. But of course, at some point, if you add stuff to a partially filled array, it's gonna hit the maximum size, and what do you do then? So the little magic trick that it does is when the array is filled, the vector allocates a brand new array, double size the original one, copies all the elements over. Every single element in the old array gets copied into the new array, and then it deletes the original array. That's actually what it does in C++. Let's just kind of step through this here at the bottom of the slide. So you've got this array pointer pointing at your dynamically allocated array, and you've added some stuff to it, and at this point it's been filled up with 10, 20, 30, 40 in the 4 slots here. So if you're going to add some more stuff to it, what you have to do is dynamically allocate a brand new array. Let's see that happen here. So you'll have another pointer in one of the functions. And if I had a 4-element array, what our compiler would do for C++ is now it's going to allocate an 8-element array. And then it has to copy all the elements over. Copy the 10 and the 20 and the 30 and the 40, whatever was there before. Okay, so we've copied all the stuff over there. And at that point, you can delete the original array, and that goes away, okay? And then this array pointer, which is one of the member datas in your vector object, you set that to point at the new array. And so what array pointer used to be looking at, now you've got this double-sized array, and you have some extra space at the end to add more stuff in it. And that's actually how vectors work. So on the one hand, we say, vectors are an alternative array, but the truth is they actually are an array. They're a dynamically allocated array, and when you need to, you can just allocate a brand new array with more space when you need to. So I think that's helpful to think about. Of course, all of this is entirely encapsulated. The application programmer is not going to have to see this happen. A lot of people use vectors, and they actually have no idea that this is happening internally. But I think for our advanced programming course, I think it's useful to actually know how vectors actually work. So this is great, of course, right? It's all handled internally by the class programmer. How great is that? But, not everything's perfect because it's still a partially filled array, as you can see here. Most of the time, like about half of the array is not actually being used. And if you have an array of large structures or large objects, you could be wasting a lot of memory as you're waiting for that stuff to be filled. That's not super. And of course, the real problem is that when you do grow the array, you have to do that big copy job, copy every single element over to the new one. And if you have a really big array, like what happens if you have a size 100,000 array? Your CPU is going to be spending a lot of time on that copy job, not really doing you a heck of a lot of good. So, interesting, but some limitations. So maybe as we go forward, maybe the next chapter, we'll continue to look for maybe even better options than this. It works for a lot of situations, but it's not perfect. So maybe for some other stuff, we should have a completely different, better strategy. Now, I will say, a couple interesting things in this chapter. Programming Challenge 16.8 in this chapter, actually, the book gives you code to a starter SimpleVector class. Gives you some code for kind of a beginning vector class. And that particular programming challenge, the SimpleVector modification, asks you to add this to it. So if this sounds interesting, you might actually practice adding this feature to the SimpleVector code that the book gives. That actually is Programming Challenge 16.8. And I would say maybe to simplify it, don't worry about making it grow double size. Maybe just add one thing, right? Just add one thing to it. And I think that is actually what that programming challenge is asking for. And if you do that, that'd be a wonderful exercise to really get a good feel for what's happening inside a vector when you use one. Other thing for my students might think back to the first exam, and the programming question on the first test might have been pretty similar to this. Might have been asking for a function that receives a pointer to one array and then makes a new array, possibly bigger based on that. So I actually was kind of prepping my students for this kind of action on the first exam, and my students might go back and review that. Would be great. And then you could do this programming challenge. Okay, so that's actually what's happening internal to vectors, and the technical name for that is, again, a dynamic array, or in other languages like Java, you'd call this a list array. Okay, and there's this other thing in the book chapter 16 for the edition that we're using called exceptions. This is such a huge story. We don't have enough time to treat this properly, but maybe you'll deal with this in one of your future courses in more detail. So exceptions in object-oriented programming are an advanced method of error handling. Our error handling that we've been doing in our course has been, just count out an error message, or return -1 or something like that for an error, or just terminate the program with the exit function is what we've been doing. So exceptions are a more advanced way of handling errors. And what happens is if there is code with an exceptionally bad problem, you can use the keyword throw to signal an error. So again, throw is a keyword in C++, shows up in boldface. Throw with a particular code for what type of error is happening. And then when you do that, all the functions in the program do get terminated unless one of the calling functions has what's called a try-catch block to detect and handle the error. So for what it's worth, the try part is where you're calling functions that may possibly throw exceptions, and the catch part is the part that actually detects that and then handles the errors and fixes it up so that the program can keep running. If you see a try-catch block, it's going to kind of look like an if-else statement a little bit, but it's working hand in hand with some code that might possibly throw an exception, is what it's called, to detect that and fix the problem. As one example, and we kind of briefly mentioned this at a prior date, the new operator in C++, when you use new for dynamically allocated memory, dynamically allocating an array or a structure or an object or something like that, it will throw an exception. It's designed to throw an exception called the bad allocation exception, bad alloc for short, if the system's out of memory. So in the rare case where you are basically using up all the memory in your system and you try to dynamically allocate an overly large block with new, see, the new operator will detect that, throw this exception, and probably it's just going to terminate your program. But if you had a try-catch block, you could detect that, throw up a message to the user and say, I'm sorry, I don't have enough memory to do that. And then you could go on with the rest of the program and maybe do something else. So that, again, that's a really big topic there. Chapter 16 does go through the details, so feel free to read that if you want, that more detail in the book. And there is this example of a SimpleVector class in there that does actually have usage, does actually use the throw keyword to throw an exception like this. And you can see what that actually looks like in that example would be smart. Okay, so exceptions. Again, you work on professional code, you'll probably have to handle exceptions, and that's a larger story that we'll leave for another course. All right, so that's our very brief, admittedly, brief overview of Chapter 16 on templates, right? Templated functions, templated classes now that allow you to get a lot of work done by abstract data types. Your functions and your classes can work on an abstract data type. The class programmer, right, is providing this option, doesn't even know what the application programmer wants to use for these things, makes the incoming data type with parameters an abstract data type to work with anything, and then the application programmer can choose what they actually want to use. Okay, very, very powerful. So for full details, I would recommend reading book chapter 16. For my students, you can skip the part about exceptions. I'm not going to be testing on that. I'm more or less leaving that for future courses. But the information on function templates and class templates, you will want to read that. And again, we do have review questions at the end of the section. And for my course, this is the last programming challenge that I actually assign for the first year sequence. It is in chapter 16, and it does use a class template, and it also does use inheritance at the same time. So the example in the book that uses inherited templated class, you kind of want to look at very, very closely to see what that's going to look like in your last assignment. And I think that's a pretty good, pretty sophisticated assignment that practices a number of things we've been talking about recently. All right, and then the lab, to kind of get a little bit more practice at this before that assignment, I'd get together with my students, and in chapter 16, there is this code for what they call the SimpleVector class. It's specific code, it's a class template, so it will save any kind of data, right? A large number of data points if you want. And what it's giving you here is it's giving you a little taste of how the STL vector works. It's not the whole thing, of course. The standard template library vector, very, very complicated, lots of great features. So kind of to cut that down to size, we have this SimpleVector example, and we do have complete code to that in the Gaddis textbook. So we get to look at that, kind of think about how that works, read that specification, and like we normally do, write a test driver to confirm that we can make one of these SimpleVector objects and store a bunch of data in it. And what I normally do is I ask my students to please, test this at least 3 times. Make 3 different simple vectors that store different types of data, and maybe make a simple vector of type integer and make sure that works. Make a simple vector of type float perhaps, and make sure that works. You know, we could make a simple vector of type feet inches, a simple vector that stores a bunch of these feet inches measurement objects that we first saw back in chapter 14. That would actually be a great exercise to do that. So again, even if you don't have the book, hopefully you can think about what that would look like. And maybe you could use the STL vector. So if you don't have access to the Gaddis book, maybe just do this on yourself. Just do this yourself. Maybe look up online how the STL vector works and maybe practice with that would be smart. I think that would be a great exercise. So when we come back next time, we're going to get into chapter 17. We're going to get into some of these options for storing a bunch of data. And again, we said, I think in the last video, we said among the strategies for storing a bunch of data, the first and most basic option is always an array, of course. But the second kind of interesting option that's totally different is what's called a linked list, where instead of one single large block of data, which is what an array really represents, you can have a whole bunch of separate little pieces that are all connected with pointers. And so that gives you a lot more flexibility and has a lot of advantages where the arrays kind of have a lot of restrictions. So linked lists, incredibly important when you get to your data structures course. It's the primary second way of storing a bunch of data, totally different from arrays. So I really hope you'll join me for that, and I'll see you then.